Let me prove this identity. Well, it's rather complicated, and you can read it carefully. Okay, this is left hand side, this is right hand side. Okay, now this formula is not a reduction formula. Now, let me show you a reduction formula. Okay, if we want to develop the reduction formula, this is the way, right? X n e to the ax dx is equal to the integral x to the n d e to the ax over a, right? Yeah, that is e to the ax dx. Now then we can use it by parts, u dv, right? This is u, this is v, okay. E to the x minus v du. V is this, right? V is this. Du would be n x n minus 1 x. So that one is equal to x n e to the ax a. I'll take the constant out, n over a, right? Then integral e to the ax times x minus 1 dx. Yeah, that is the reduction formula. Minus n over a times I n minus 1. See, this is I n. So that is the reduction formula. Not this one. This is the result of the integral, rather. So we want to prove this one. Well, this is not a formula, but rather a reduction formula. Yeah. Okay. Now let me do the proof. Well, I'm using mathematical induction. Okay. First, uh, when n equal to 0, when n equal to 0, the left-hand side is x to the 0, right? E to the ax dx. That one's easy. This one's equal to e to the x. Plus, okay, that's left-hand side. The right-hand side is equal to e to the ax over a sigma k from 0 to 0, and next one to the k, n factorial, n is 0, 0 factorial, n minus k factorial times n 0 minus k, a to the k plus c. Then this will go to e to the ax over a. This is equal to minus 1 to 0. 0 factorial, 0 minus 0. This is 0, n is 0. And x 0 minus 0, a to 0 plus c. Well, everything is 1, so this will equal to e to the ax over a plus c. So the right hand equal to the left hand. So conclusion is it is true for n equal to 0. Right? And then the second step is assume it is true for n equal to m minus 1. That is to say, the integral m minus 1 to the e to the ax dx, that's the left-hand side, will be equal to assume is true, n equal to m minus 1, right? So equal to e to the ax and over a sigma k from 0 to n minus 1 and minus 1 to the k n minus 1 factorial n minus 1 minus k factorial and n minus 1 minus k over a to the k plus c. Well, simply we replace n by m minus 1 if this is true. Okay, assume is true. Then uh, then we want to show that it is true for n equal to m. Right? Yeah, that is the induction. Okay, we let is true when n equal to m minus 1. We want to show that it is also true when n equal to m. Okay. Okay, now let's show. Okay, continue. I am, now we have a reduction formula. I am equal to x m e to the ax over a minus m over a times I m minus 1. That's the reduction formula. And we have an assumption already that m minus 1 is this. M minus 1 is this. It is true, right? It is true. So this one is equal to, so I m is equal to equal to x m e to the a x over a minus m over a multiplied by this. This is supposed to be true. And it's equal to e to the ax over a sigma k equal to 0 and minus 1 to k and m minus 1 factorial m minus 1 minus k factorial x m minus 1 minus k a to the k plus c. Well, we simply use this, right? This is supposed to be true. Now and then, lots of writings. It's e to the ax over a. No, not. We have a common factor. I take the common factor out. Yeah, that's the way. Sorry. So left to the x to the m. This is left over minus. This is taking common factor out, and m is nothing to do with k, so we can multiply by this one into the sigma notation. This is k equal to 0 to n minus 1. This is out, common factor. M times this one is m factorial. This time this one's m factorial. And then n minus 1 minus k factorial x n minus 1 minus k. A times this one is a k plus 1. Let's see. Wow, okay. So far, so good. And then, we let j is equal to k plus 1. We let j equal plus 1. Then j, no, small j, j, when x equal to 0 will be equal to 1, right? When x equal to 0 is a 1. And j, when x equal to m minus 1, when k equal to m minus 1, then this is equal to m, isn't it? Yeah, based on this. Okay, then my im replace j, okay? So this one equal to e to the ax. I have to copy carefully. This will be x to the m minus. Now I replace k by j, sigma k equal to 0, j is equal to 1, right? So j equal to 1. When k equal to m minus 1, j equal to m. And minus 1 to the k. What's the k? K is j minus 1. So far, so good. And this is m, right? M factorial. M minus 1 minus k is m minus j, right? Because j equal to k plus 1 factorial. Then this is x. K plus 1 is j. M minus j. A to the k plus 1 is j. Yeah. Good. Now, I don't like a j minus 1, right? J minus 1 just changes the negative sign. So this is im equal to e to the ax j, ex over a, x to the m. Now, if I write it j, forget negative one, this will be changed to positive, right? This is plus sigma j equal to 1 to n minus 1 j. Okay, change. And then n minus j factorial x n minus j a to the j. Wow. Yeah. What happened when this series j equal to 0? J equal to 0. Then this series actually means negative 1 to 0. And m factorial n minus 0 factorial x n minus 0 a to 0. So that means this when j equal to 0 is equal to xm. What do I mean is this is nothing but the series j equal to 0. I'll repeat again. This term x to the power m, x to the power m is just one term in the series when j equal to 0. So therefore, Im is equal to e ax over a. This one is a j equal to 0. So this one equal to j equal to 0 to m negative 1 to the j m minus j factorial a to the j x m minus j plus, yeah. Now let's check this formula. This formula is equal to for j and a k, they are just dummy variables, right? So this formula we want to prove is same as formula as this. Just k and a j, different notation. So it's true for j equal to n equal to n. Yeah. When n equal to m, it's also true. That's exactly we want to see. We want to show that it's true for n equal to m. So we did show that. We did show this is true. Therefore, this formula is true for all n. See? Let me save writing. It is true that this is true for all n. Is a positive integers. Well, I think it's good. Well, let's have an example. So the formula has been proved. Let's have an example. This example, x to the power 6 e to 2x dx. So the formula has been proved. We just use this theorem to do one example when n equal to 6. So this one equal to, according to the formula, is equal to 2 over 2 e to the 2x, right? Then sigma k equal to 0 to 6 1 k 6 factorial 6 minus k factorial and x to the 6 minus k a to the k plus c. Wow. See, we can use the theorem, the formula now. So this will go to 2 e to the 2a and the series, right? The first term is 0, is 1, therefore is equal to 6 factorial. This is 6 minus 0 factorial, and x to the 6 minus 0, 2 to 0, right? That's the first term. And the second term, negative, right? Negative 6 factorial. This is 5 factorial, right? Then x to the 6 minus 1, this is 5. And 2, a is 2, k is 1, right? And third term, is is 6 factorial and 4 factorial, and 6 minus 2. This is 2 to square. Yeah. Then minus 6 factorial, 3 factorial, and x is 6 minus 3, and 2 to 3. Yeah, and then plus 6 factorial and 2 factorial, x is 6 minus 2, and 2 to 4. Then minus, it's just no, they use the formula. It's quite tedious. So this is 6 factorial, this is 1 factorial, and x is 6 minus 1, right? And 2 to 5. And finally, this is equal to 6 factorial and 0 factorial, x to 6 minus 0, 2 to 6, yeah, and plus c. Then after the calculation, we get to x, I'm sorry. So, yeah, 2, a is 2, huh? 2, and just calculations, this is x is 6, and minus 3x is 5, plus 15, minus 15x cubed, 45 over x squared, minus 45 over 2x, plus 45 over 4. Well, this calculation is secondary. Okay, so it's a nice way to prove it. Proof is the topic today. The calculation is trivial. So I hope you like this. Thank you.